Hello everyone, welcome back to NEET World. So today we will be discussing the continuation to the previous session on structure of atom. So we will be discussing Bohr's atomic model, everything clearly regarding that, and after that we will be moving for de Broglie hypothesis. Okay, right. Let's start our session with Bohr's atomic model. Okay, so now in Bohr's atomic model, what we need to look here? Definitely there will be one question in your EAPCET exam from this Bohr's atomic model. You just open the previous papers and you can just check them. Almost if there are 100 questions from Bohr on structure of atom, there will be at least 70 questions are from, or 50 plus questions are from this Bohr's atomic model itself. Right? So that is how it is very important. And after this quantum numbers, and then after this you can prioritize Heisenberg's uncertainty principle and de Broglie wave equation along with the photoelectric effect. These are the topics that must be focused from structure of atom when it comes to EAPCET entrance exam. Okay, right. Look at here. What Bohr's atomic model says here. See, we know there are some limitations in Rutherford's atomic model. What are the limitations we have? Right. First one is unable to explain stability of atom. It is unable to explain stability of atom. These are the drawbacks of Rutherford's atomic model, and does not explain energy levels. Energy levels were not explained in the Rutherford's atomic model. And the next one is spectra is not explained. So these are the three main drawbacks, right? So by looking at the drawbacks of Rutherford's atomic model and by utilizing the Planck's quantum theory, Bohr proposed Bohr's atomic model. So now when he proposed his atomic model, to understand it very effectively, we have some postulates to look into it. Okay, so by looking at the postulates, we can understand this Bohr's atomic model very effectively. Look at this. So what he told is, electrons revolve around the nucleus, in a circular path called orbits. Okay, so if this is a nucleus, around this nucleus electrons will revolve in a fixed path. So these fixed path or circular paths are called orbits. What we can call this as orbits. Okay, so now these orbits can have fixed energy. See, the circular paths are what? Orbits. So these circular paths have fixed energy and fixed radius. So these orbits have fixed energy and fixed radius. Okay, therefore we can call these orbits as stationary states also. Okay, so these circular paths we can call as orbits or stationary states because they are having fixed energy and fixed radius. Now next postulate is, what he told is, during the revolution of this electron around this nucleus, there will not be any emission of energy or absorption of energy. Okay, therefore an electron will be revolved in the circular paths only, without, it won't emit energy or absorb energy. He told like this. And the next postulate, if in case if an electron is absorbing energy, then what happens? If in case electron is absorbing energy, then that electron will excite to the next higher energy level. For example, an electron here it is in lower energy state. Let us say it is in this energy state. Now if in case it absorbs energy, then it jumps to the next higher energy level depending upon the how much amount of energy it is absorbed. Okay, so now what I can say, so by absorbing the energy, electron is exciting to the next higher energy level. Now there is one more scenario here. Electron can release the energy or emit the energy. So when it is emitting the energy, it means electron is losing its energy now, therefore it goes to the lower energy state like this. Okay, right. So when absorbed energy is there, if we analyze the spectrum, we will get absorption spectra. Okay, and when energy is emitted by this electron, when it is going back to the lower energy state, energy will be emitted. Then during that emission, will if we analyze that emitted energy, then we will get emitted spectra. So this particular postulate explaining absorption and emission spectra of this atomic model. Okay, so this is one of the very good explanation for spectra. Okay, and we know from quantum theory, what we know, the emission of energy takes place in discontinuous manner. Yes, so that is why by utilizing quantum theory he explained this spectra condition. Here we can understand. Okay, hope this this postulate is also clear. Right, now what is the next postulate? See, everything is written here, all the postulates are written here. So just listen to my oral sentences, whatever I am giving to you, so that you will get this complete clarity here. See, what is the next postulate here he considered is, only those circular paths are allowed whose angular momentum L is an integral multiple of h by 2 pi. Okay, so it means n value can be integer. Okay, 1 2 3 4 like this. Okay, so O's angular momentum is equals to h by 2 pi, and h by 2 pi I am writing. Then we can say that particular orbit is allowed. Okay, now how can we take the angular momentum for this particular circular orbits? See, if electron is revolving here, see, it is moving in this direction from a distance r from the nucleus, having some theta here. So what is the theta here? 90 degrees, right? So L, angular momentum L is equals to electron having some mass m, moving with some velocity v at a distance r from the nucleus r. Okay, and then next with some theta, sine theta, that is sine 90 I am taking here. Sine 90 is 1. So angular momentum L equals to mvr. Sine 90 1. So mvr will be equals to nh by 2 pi. So this will be the condition we got finally. So by looking at this equation, this is one of the very important equation here. From looking at this equation, see, you can get radius of an nth orbit, you can write it as nh by 2 pi rn. Right now 2 pi mv you can write, like this you can write. Okay, so here we represent velocity of electron revolving in the nth orbit, and radius of that nth orbit is given by rn, like this. Okay, so now what is this n value here it is indicating? See, n value indicating here, so if this is first orbit n equals to 1, second orbit n equals to 2, and say third orbit n equals to 3, like that. Okay, so these n values later called it as principal quantum numbers. What I am saying, they are called as later these n values are called as principal quantum numbers. See, whenever there is a blur on screen, you just tell me so that I will adjust here, those who are in the live session. Okay, right. Yeah, just a minute. Just a minute, I am just adjusting this screen. Yeah. So now look at this. What I am saying, Rn, radius of an nth orbit is equals to nh by n 2 pi mv I am saying. So mass m represents mass of electron, v is velocity of electron, r is the radius of electron. Now by simplifying this, we are going to get some mathematical outcomes. Now how can we simplify? What are the methods to use to simplify this? Already I have made a special video on discussion of this Bohr's atomic model. Anyways, we are focusing for EAPCET. Let us go directly to the formulas and directly on the questions. If you really wanted to know the derivation of this radius, like radius of an nth orbit can be written as Rn equals to 0.529 n square by z I am writing. So this is the formula in terms of angstrom units. Okay, now how we got this constant value, all these things are explained previously itself, so I do not want to again discuss the same thing here. Okay, you just search Bohr's atomic model by Ajay Sir, NEET World, you can search, you will get complete derivation related to this Bohr's atomic model. Now as of now, let's look into the questions. Okay, so first of all, see, these are the postulates, you can read it once, whatever I have discussed, everything will be there here. Okay, and next, so this is the radius formula we got. See, for the radius of first orbit of hydrogen atom, if I ask, what will be the case here? I am saying formula will be 0.529 n square by z. This is in terms of angstroms and this is in terms of picometers. Okay, so now look at this. I am asking what is the radius of electron revolving in the first orbit of hydrogen atom. So n value first orbit na n value 1, okay, and hydrogen atom z value also 1. Therefore R1 of hydrogen will be equals to 0.529 into n square. N is 1 and z is also 1. Therefore 0.529 angstroms is the radius of first orbit of hydrogen atom. So here you can see, you can also give that answer of 59.9 picometers as your answer here. Okay, right. Hope this is clear. Let me go forward with few more things to discuss here. Next here, what will be the radius? What will be the radius of first orbit of helium ion I am writing? See, have you observed? I have given hydrogen atom, but here helium cation I have given. Why? Because this Bohr's atomic model is applicable only for single electron system. It should contain only one electron, then only this Bohr's atomic model is applicable. Okay, it's not applicable for multi-electron system, applicable only for single electron system. It means we cannot calculate for helium atom here using Bohr's atomic model formulas, but we can calculate it for helium ion because helium ion contains one electron, right? Now R1 of helium, that is 0.529 into n square. N square, what is the n value here? 1. And what is the z here? Atomic number of helium is 2. So this is nothing but 0.529 by 2. Okay, so now I can simply write R1 of helium ion is equals to R1 of hydrogen atom by 2. Okay, this will be the relation between hydrogen atom radius to the helium ion radius. Now similarly, if I ask you for what is the relation between radius of first Bohr orbit of lithium plus 2 ion and first Bohr orbit of hydrogen atom, tell me what should be the answer. See, simple now. What is the formula I given? Radius is equals to, radius of nth orbit is proportional to n square by z. So here n value is 1 in all the cases I have mentioned R1. So only z is changing. So R1 of Li plus 2 is equals to, R1 of Li plus 2 equals to R1 of hydrogen atom divided by z value of this lithium is how much? 3, right? So you can take here it as 3. That's it. Hope this is clear whatever we are discussing here, right? So there are multiple questions asked on this radius if you look into the previous session papers, okay? And guys, you know, in the last year itself, I mean the last year also for EAPCET 2025, we have covered PYQs of past papers, as well as, you know, in our channel we already covered 2025 TS EAPCET question papers are discussed. Very effectively we discussed for TS EAPCET 2025 papers. Last year papers are already discussed. You just go and watch these sessions if you want to practice more number of questions, or direct question paper if you want to look. Just go and look into this playlist of this NEET World channel where we discussed everything in the live session. Okay, right. We covered both by PC papers and MPC papers. Okay, right. Someone here in the comment box asking something, let me check. Right, next one here. So if I ask you what is the relation between R1 of hydrogen and R2 or R3 of helium plus ion, what could be the answer? See, R1 of hydrogen is nothing but 0.529 now, that's it, okay? And R3 of helium ion, if I ask, what can be the answer? So R3 means n value here 0.529 into n value given as 3, n square is 9, by helium ion is how much? Atomic number 2, that's it. So you can say 9 n square by z means n square by z, n is 3, so 9 by 2 into this 0.529 is nothing but R1 of hydrogen. Why I am specifically discussing these kind of questions? Because now I will show you the questions that are appeared in the previous papers. Look at this. Look at this question. The ratio of radius of second orbit of helium to that of third orbit of beryllium they are asking. Very simple here. What could be the answer, you tell me? See, radius of second orbit of lithium they are saying, Li plus 2, to the ratio of third orbit of beryllium they are saying, beryllium 3 they are asking. See, what will be the radius formula? We know 0.529 n square. What is the n value here given? 2 square, that is 4, and atomic number of lithium is hydrogen, helium, lithium 3, right? You can write here n square by z is over. Next, here also we have 0.529, and what is the n value here given? 3, so 3 square 9, and what is the atomic number of beryllium? 4, you can write. Okay, right. So that from here what you can get? 4 by 3 into 4 by 9, that's it. So we will get 16 by 27 will be equals to R2 of lithium plus 2 by R3 of beryllium. So what they are asking? Ratio only now. So this ratio is how much now? 3 of Be plus 3, that's it, 16 by 27. Option D will be perfect answer here now, right? Hope this is clear how simple questions are asked. See, even in JEE also we are seeing this kind of questions. So both, if you are preparing for either JEE, NEET or EAPCET, you can have a practice on this kind of model questions. Very basic questions, right? Right. Now tell me what could be the answer for this question. What is the radius of fourth orbit of electron in fourth orbit here, beryllium plus 3, to the R4 of lithium plus 2 ion? What will be the answer for this question? So I want this ratio in the chart box. Okay, so whatever the way I have explained, use the same way and can give your answer in the chart box. Okay, right. Next here, look at this. Look at this question. Look at this question. What is the difference in radii between 4th and 3rd orbit of helium ion? So you can easily answer whatever the way I have explained. You can use same method here. So what could be the method here? So radius can be taken as 0.529 n square by z we are saying now. So for difference between the radii of 4th and 3rd now, so it means z value here it is same, so take z out, and this is difference between 4th and 3rd, so 4 minus 3rd or 3 n square, that's it. So use this formula now and you can get one of these options. Tell me what will be the answer for this particular question in the comment box. This is in angstrom units you are going to get. So now 1 angstrom equals to what? 1 angstrom equals to 10 power minus 10 meters now. Yes, you can use this here, 10 power minus 10 meters, to get your final answer, and tell me your answer in the comment box for this particular question also. Okay, hope this is also clear. Right, practice more number of questions for getting more clarity on the concepts. Radius is completed now. Now we have radius is completed. Now we have velocity formula. So what do we mean by velocity here? See, again mvr equals to nh by 2 pi we have seen. From this v I can write nh by 2 pi into mr right now. So now what is the r value we have seen? nh by 2 pi m. R means you have seen some constant like 0.529 into n square by z. So I am writing z in the numerator. So this n and this n square is getting cancelled out. So remove these constants. So value of velocity of an electron revolving in the nth orbit can be given as some constant multiplied with z by an. Hope this is clear what we are going to get. See, 2.18 into 10 power 6 z by n. Look at this option, like this formula which I have already given. So this will be the value of constants. By simplifying this, we will get 2.18 into 10 power 6 z by n meter per second. Okay, now tell me what is the velocity of electron which is present in the first Bohr orbit of hydrogen atom. So you can take 2.18 into 10 power 6 z for hydrogen atom is 1, and present in which orbit? First orbit. Okay, it is also 1. So meter per second, that's it. So 2.18 into 10 power 6. This will be the velocity of first Bohr orbit of hydrogen, electron in the first Bohr orbit of hydrogen atom. Now there will be a question asked previously. What is the ratio of electron revolving in the first Bohr orbit of hydrogen atom to the velocity of light or speed of light? What will be the ratio they are asking? Very simple. We know speed of light will be 3 into 10 power 8 meter per second, right? And velocity of first Bohr orbit of hydrogen atom electron in the first Bohr orbit is 2.18 into 10 power 6 meter per second. So by simplifying this, what could be the answer here? 300 by 2.18. So this will be giving us around 137. Okay, so it means velocity or speed of light will be equals to 137 times faster than the velocity of electron in the first Bohr orbit of hydrogen atom. Okay, so this is a question which is appeared in the previous exams. Okay, right, hope this is clear. Right, let me move forward here. Next, let me give you few more questions related to this. So now tell me what is the velocity of electron moving in the second Bohr orbit of beryllium plus 3 ion. So what could be the answer? Again take 2.18 into 10 power 6 z by n meter per second. So 2.18 into 10 power 6, z is how much? Atomic number of beryllium is 4 and n value given as 2, second Bohr orbit is given, that's it, meter per second. So 2 times, so it will be 16, 3, 4 into 10 power 6 meter per second. So this will be the velocity of electron revolving in the second Bohr orbit of beryllium plus 3 ion. Okay, right. Let me move forward with few more questions. Yeah, what will be the answer for this, you tell me? Ratio of velocity of electron in the first Bohr orbit of helium plus to the velocity of electron in the second Bohr orbit of lithium plus 2. What is the ratio for these two things? Tell me in the chat box. Okay, you just give a try and you can answer me in the chat box. Hope you can easily solve this question because you are clear with the concept that we are using here. So just what to take? Ratio you take 2.18 into Z by N in the numerator, same thing in the denominator, substitute the values, we will get a answer upon simplification. Okay, tell me that simplified answer in the chat box. Hope you are clear with this concept. Now we have one more. First one is radius over, the next velocity also over, the next we have energy. Okay, so now energy, or I can say total energy. So energy is given as minus 13.6 Z square by N square electron volt per atom. This is one important formula. In the same way, with different units, we have different formulas here. Look at this, 2.18 minus 2.18. Why this minus symbol? I will tell you. So minus symbol indicates there is a significance for that. For example, an electron is present, independently existing electron is present here. So consider its energy is 0. From this state, its energy is how much I am saying? 0 energy state, let us say. So now we know more energy means less stability we know. If a species is more stable, then its energy will be in the lower state right now. So this electron, when it is present with the nucleus, whether it is very closer, it means if it is very closer to the nucleus, more stability it has. Okay, it means an electron present very close to the nucleus can be having more stability, we can say lower energy state. That means in the hydrogen atom, if you put this hydrogen atom, atomic number is 1 now, 1. And in the first shell, if I say N value also 1. So energy will be equals to how much now? Minus 13.6 Z square electron volt per atom. It means the electron present in the first Bohr orbit of hydrogen atom will be more stabilized or more stable by decreasing its energy by 13.6 electron volts when we compare with an independent existing electron. Okay, I hope this is clear. 6 electron volt. So what is the ground state energy level of hydrogen atom? 13.6 electron volt. Similarly, if I say electron is present in the second state of hydrogen atom, okay, N value is 2 I am saying. So if it is second energy level, so E becomes how much now? Minus 13.6 Z square. Z is how much here? Atomic number hydrogen 1 and N value 2 I am saying, electron volt per atom. So in this way, what will be the answer? 2 1s the N square now, so it will be 4. So it will be 3 times 1 we have 0.4. So the first energy, see ground state N equals to 1 and the first excited state or second energy level, we can say its energy as 3.4. See what you are observing here. So 13.6 minus 13.6 minus 3.4. As electron moving away from the nucleus, this will be the scenario when electron is very close to the nucleus in the first state, and when it is in second energy level, it is minus 3.4. So as electron is moving away from the nucleus, its energy is increasing, stability decreases. Okay, and if I say electron is present at an infinite distance from the nucleus, if at infinite distance, N value becomes how much? N value is infinite now. So something by infinite means 0. So it means that is at 0 energy state. Okay, so this is what you need to know here, right? Yeah, let me discuss further here. So what are the formulas we have? Energy means minus 2.18 into 10 power 18 z square by n square joule per atom. Okay, and this is in electron volt per atom. Here you can say kilojoule per mole it is. It is per atom, it is per mole. And in the exam, most seen questions are on this joule per atom, electron volt per atom. Okay, so you should focus on this. First formula is what? Minus 2.18 into 10 power minus 18 joule per z square by n square joule per atom. And one more is minus 13.6 z square by n square joule per atom, electron volt per atom. These are the two formulas you should focus. Now what we discussed, the ground state energy is at minus 13.6, and when I go for second energy level, that is first excited state also we can say, it is having minus 3.4. Similarly, if I say energy of third state of hydrogen atom is how much if you ask, so you can take minus 13.6 z square. Z square is how much? Hydrogen 1 by n square. N is 3 square. It becomes 9 electron volt per atom. Upon simplification, you will get minus 1.51. Okay. Similarly, for E4, it is 0.85, E5 0.54. If upon going up to infinite, we will get energy as 0. Okay. If you observe, this is the energy coordinate we can consider. So as we move away from the nucleus, the energy of electron present in an nth orbit is increasing. Energy increasing means stability decreases, you can understand. Now as n value increases, what happens? As n value increases, energy also increasing. Okay, but energy gap is what happen? Energy gap between these levels is getting decreased. This is a statement based question you can expect from here. See, energy gap here it is 10.2 and here it is just 1.89, it is 0.66. So what we are understanding, see, for energy difference between first and second energy level is maximum. As n values increasing, their energy gaps are getting decreased. So as we move away, away from the nucleus, they come very close, they become very close. Okay, that energy gap is very small. Okay, initially it will be very big. Okay, hope this point you can note in your books. Next, there are few other formulas to be noted. We have something called a time period. Okay, see, we know electron is revolving around the nucleus now, so we can calculate time period of revolution of an electron in its orbit. How much time it is taken for one revolution or like that. See, what is the formula? If electron is present in an nth orbit, you can take n cube, that orbit number to the power 3 and atomic number of that particular atom. Okay, for example, hydrogen atom, if it is 1.5 into 10 power minus 16 n cube, present in second orbit if I say, so 2 cube and atomic number is 1, that is square, that is same only. So T becomes what? 1.5 into 10 power minus 16 into, this is 8. Okay, so this will be the time period in seconds. This value is in seconds. Okay, similarly, frequency of revolution. So what is this frequency of revolution? That is nothing but inverse of our time period. So you just write F is equals to frequency of revolution is equals to 1 by T. Okay, so by simplifying this, you can get 6.6 into 10 power 15. This becomes reverse, z square by n cube. Z square by n cube. So here I can write second inverse. Second inverse also can be written as hertz now. Yeah. So you can indicate with second inverse or hertz for the same thing. Okay. Now tell me what is the value there. What is the frequency for this? 6.6 into 10 power 15. Atomic number for hydrogen atom, if I say 1, the next n value I have given it as 2 cube, that is 8 only. So 6.6 into 10 power 15 by 8. So this will be the value for your time frequency of revolution, I can say. Okay, right. Let's move forward. If you look at these questions, these are from photoelectric effect. What we discussed in photoelectric effect, see, there is a metal surface on which energy is incident. Okay, if that energy is sufficient to eject this photoelectron, this electron from that metal surface, then we can say photoelectric effect right now. So the minimum amount of energy required to eject this electron is called threshold frequency in terms of frequencies, or I can say work function in terms of energies, work function. Okay, now look at this. Work function values for 6 metals are provided here. This is a minimum amount of energy required to eject the electron from this particular metals. Okay, and look at the statements given. How many of the above metals do not eject the electron when they are made to strike with a radiation of wavelength 400 nanometers? So simple, you take lambda equals to 400 nanometers. So what you can use here, so here you can use energy is equals to 12400 by lambda. Okay, this is in angstroms. Okay, so by using this relation, you will get to know this is in angstrom, that is in this is in nanometer, that is in angstrom. So you just convert into angstroms and simplify, you will get one of these options. Okay, how you get to know? So you will get some value now. If that value, this answer will be in terms of electron volt. Okay, so if you are getting this value greater than these values, then photoelectric effect is observed. If it is lesser than these values, no photoelectric effect is seen in those cases. So based on this, you can easily answer this right. Look at this. This is related to Bohr model. So we will solve these questions. The ratio of ground state energy of lithium, helium, hydrogen are given like this. So choose the perfect answer for this. See what we know, energy formula minus 13.6 Z square by N square electron volt per atom. Okay, so this 13.6 is common in everything, every case, lithium, helium, everything it is common because it is a constant. Now take only lithium plus 2 ratio, helium plus and hydrogen. Okay, so Z square for lithium is how much? Z square, atomic number is 3, square 9 by ground state they are saying, hydrogen like N value is 1. For helium it will be 2 square 4 by 1, and for hydrogen it will be atomic number 1, its ground state means N value is also 1. So what is the ratio we got? 9:4:1, that's it. So where do we have 9:4:1? Option C. Simple, right? So this is a question asked in AP EAPCET 2024 paper. Okay, now look at these next questions. Before going to further into the questions, now look at, we have something called spectrum here. So what is the spectrum? First of all, we have discussed a postulate. When an electron absorbs energy, it excites to the next higher energy level. Okay, so the energy that is absorbed by this electron, if we analyze, we will get absorption spectra. So what is this absorption spectra looks like? How this absorption spectra look like? See, very simple. Here I have hydrogen atom. Look at here. I just want to explain you this absorption spectra and emission spectra. Now I am passing a light here of different wavelengths, and here I am placing one photographic plate. What we are placing? Photographic plate. So we are passing the light, and that is incident on this hydrogen atom. Now hydrogen atom will absorb a suitable frequency that is useful for excitation of electron. Remaining all other wavelengths will be going without any usage right now. So all other wavelengths will fall onto this metal onto this photographic plate, but there will be missing of few lines. That few lines corresponds to the observed wavelength of this hydrogen atom. So that see, all the wavelengths are hitting on this photographic plate, but only few lines are missing. So wherever the lines missing, we will be seeing darkness right now. So we can see in absorption spectra, dark lines are observed, dark lines on bright background. What I am saying, on bright background, because all the wavelengths are hitting onto or falling onto this metal, falling onto this photographic plate, but few lines were missed, which is absorbed by this hydrogen atom right now. So we'll get dark lines on a bright background. Okay, so this will be the scenario in case of absorption spectra. Now we have one more called emission spectra. So what is this emission spectra? For example, here I have the substance, okay, and to this we are giving the light, we are giving the energy. Now what happens? This absorbs the energy and excites to the higher energy level right now. So after excitation, again after some, what happens? Whatever the excited species is there, that falls into its original position right now. So when it is falling into its original position, what happens? It will emit that extra energy now. So if we analyze this extra energy, if it is falling on a photographic plate, if we analyze that, so what we'll get? See, on this photographic plate, only this emitted light is falling, no other frequencies, no other wavelength lights are observed right now, no other wavelengths are falling, just one emitted light is falling. So what we can say, now there is a dark background on which bright lines are observed. So emission spectra will be seen as on dark background, bright lines, whereas absorption spectra, dark lines on bright background. It means emission spectra and absorption spectra for a particular species will be complementary. Okay, so here dark lines will be seen, there bright lines will be seen. Okay, this is completely complementary to each other. I hope you got what is exactly emission spectra and absorption spectra and how do they relate to each other, right? Now when it comes to hydrogen atom, when I am taking hydrogen atom, when we are considering hydrogen atom, so for this hydrogen atom, there were the spectral lines observed, and these spectral lines are grouped into different states, that is called Lyman series, series spectral lines, and the next Balmer series, next Paschen, bracket, Fund, Humphare. So these are the different spectral series which are grouped into different series of lines. Okay, so now how can we say a line belongs to this Lyman series line? Okay, look at here. When an electron is falling from any higher energy state to ground state, it means n equals to 1, that line belongs to Lyman series line. Okay, and one more thing, if an electron is coming from any higher energy state to this second energy state, that line belongs to Balmer series line. Hope it is clear. See, from any higher energy state to ground state, that is n equals to 1, we can say lines belongs to Lyman series line, and any higher energy state to second energy level, that is n equals to 2, Balmer series line. Similarly for n equals to 3, Paschen series, n equals to 4, bracket, n equals to 5, Humphare, and Fund, n equals to 6, Humphare. Hope this is clear. Now see, I can say that an electron transition takes place from second energy state to first energy state, right now n equals to 1 state. That is, this line will be seen in the Lyman series line now. So we can say this is the first line seen in the Lyman series. So I can say this is first line or H alpha line of Lyman series. Okay, and similarly if an electron falling from third level to first level, that will be 3 to 1 I am saying now. So this will be also belongs to what? Lyman series line only, but this is called as second line. because this is the second possible line now. Yes, second line. Similarly, if it is coming from 4 to 1, we can say this belongs to Lyman series. 4 to 1 also, like ground state should be 1. Then we can say those lines as Lyman series lines. Hope this is clear. Like this, I can say first line H alpha line, second line or H beta line, third line H gamma line. Now why I am using this gamma, beta, all this means, or first, second line means, in the exam they will directly ask what are the n values for H beta line of Lyman series. What are the H beta values? I mean, what is the H beta line values in the Lyman series they will ask. H beta means second line now. So in Lyman series means definitely N1 should be 1 and second line should be H beta. It means if it is from 2 to 1, I can say H1 first line, H alpha. If it is 3 to 1, I can say H beta. So I hope you got what is the N1 and N2 values here. So it is 3 to 1 can be considered as H beta line. In same manner, you just tell me what is a H alpha line in this Balmer series. Okay, so we know Balmer series, the number here, lower number is Ni or N1 equals to 2, I can say. Okay, and from any higher energy state it can come to this second level. Then we can say it as Balmer series line right now. So if it is coming from just from 3 to 1, we can say this is first line, and 4 to 1, 3 to 2, I can say first line, 4 to 2, second line, 5 to 2, third line, 6 to 2, fourth line, like that. I hope it is clear. And if it is coming from H infinite number, from n value equals to infinity to 1, that is in Lyman series, then we can say that is the last line of this Lyman series. What is the first line? 2 to 1, last line infinite to 1. Okay, in Balmer also infinite to 2. Like this, we have different number of lines possible for each of this series. Okay, so what are the lines we have seen? Lyman series, Balmer, Ascent, Bracket, Fund, Hamfari. Okay, now in the exam, now they will ask like this. A question will be made in this manner. See, number of spectral lines possible when an electron falls from fifth state to first state. So how many lines are possible here? Tell me what are those lines. So now just use this formula, or I will tell you in traditional way how can we use this. See, this is n equals to 5 now, this is n equals to 1. So electron can directly comes from 5 to 1, or it can comes from 5 to 2, or 5 to 3, or 5 to 4. Okay, and again from 4 to 1 directly, or 4 to 3 directly, or 2 directly, like this we can write. And from here directly to the first, or to this second level, and then to the first level. Like this, how many lines we got? Check once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines we got. So possible number of spectral lines are how many now? 10 lines. See, always writing this many lines will be, and writing and checking will be very difficult, right? So that we have a simple formula to calculate number of spectral lines possible when an electron is falling from fifth state to first state. Just use this formula. Number of spectral lines equals to n2 minus n1 into n2 minus n1 plus 1 by 2. Okay, so what is the n2 value here given? 5 minus 1 and 5 minus 1 plus 1 by 2. Okay, so what could be the answer? So here it will be 4 into 5 by 2, it means 10. So both giving same number now, 10 and 10. Hope this concept is clear now. Okay, this formula is very important when it comes to EAPCET or JEE or NEET exams. Okay, now in these lines, we got 10 lines now. So in these 10 lines, number of lines appeared in Lyman series. How can you answer this? See 1, 2, 3, 4. So 4 lines are in Lyman series, and similarly number of lines appeared in Balmer series. See 1, Balmer series means it should fall into the second level now, n equals to 2. 1, 2, 3. Okay, so here I will tell you one trick to calculate this. Number of lines in Lyman series, if they ask, you just take you can use this formula n2 minus 1, because the n value, the value of Lyman series any level to first level now, so that's why n2 minus 1 you can see. And next, if they are asking for Balmer series, that higher energy level, I mean whatever that highest energy, fifth level n2 value here is 5 now, so n2 minus 2, because Balmer series now. Like that, if they ask for past chain, that is third energy level, n2 minus 3. Like this you just check, you can get the exact answer. See, Balmer series how many lines? 1, 2, 3. That's it. Here also 5 minus 2 means 3. Working now. And past chain series 1, 2. It means 5 minus 3, 2. Yes, this formula is working now. You can use for finding number of possible spectral lines and number of possible spectral lines in each series. I mean Lyman, in Balmer, and like past chain bracket, like this. Hope everything is clear regarding this spectral lines concept. Right now? Right. Yeah. Next, one more last formula related to this we have here is asking about energy change when an electron falls from higher energy state to lower energy state. Okay, so first one is asking about a wavelength. Look at this, 1 by lambda, this is also called as wave number, which is equals to RH z square into 1 by n1 square minus 1 by n2 square. Okay, this formula we can also say it as Rydberg's equation. What I am saying? Rydberg's equation. What is the use of studying this formula? Just now we have seen electrons are falling from higher energy state to lower energy state now. So in this case, what is the energy difference change or what is the wavelength change during this process can be calculated using this formula. Okay, so now what is this RH means? It's a Rydberg's constant. You can take its value approximately as 1.1 into 10 power 5 centimeter inverse, in terms of centimeter inverse I am saying. Okay, right. You can substitute here. What is the Z value here? It's an atomic number. If it is hydrogen 1, helium ion if it is 2, lithium plus 2 ion 3, like that you can take the Z value. Okay, hope this is also clear. Hope everything is clear. Just mention clear if everything is clear. If everything is clear, just mention clear in the chat box. Let me make one question related to this wave number. See, the wave number of first line of Lyman series, first line of Lyman series of helium ion is X. Then what is the wave number of second line of Balmer series for Be plus 3 ion. In terms of this X we need to answer. So this is again EAPCET question only. Whatever the questions I have taken, all these are EAPCET questions that will be really helpful for even for JEE NEET preparation also. Okay, so for whatever the exam you are preparing, you can practice these questions, you can attend these sessions. Okay, so how can you calculate? Wave number means nu bar, which is 1 by lambda, which is equals to RH Z square. What is Z square? Given for helium now, so Z means helium 2 square 4. Okay, 1 by N1 square. What is the all first line of Lyman series? Just now I have explained clearly about first line, second line, all these things. Lyman series N1 equals to 1, and first line that should comes from second level to first level, that's it. So N2 is 1, N1 is 2. So here you can use N1 square minus 1 by N2 square. So what is N1 and N2 values here? So N1 is 1 and N2 here is 2, that is 4 here. Okay, right. Nu bar will be equals to RH. The next what will be getting here? So it will be 4, LCM is 4, here we have 4, 4 minus 1 is 3, that's it. So this 4 can be cancelled, nu bar will be equals to 3H. Okay, so this is equals to how much they are saying, which is equals to X. From this what I can say, RH value can be taken as X by 3. Okay, right, we got Rydberg's constant value here as X by 3. Now we can substitute this for the second number, therefore we will get. So for this beryllium, nu bar will be equals to what? 1 by lambda, which is equals to again RH. Beryllium atomic number is how much? 4. Z square, 4 square 16 here you can write. 1 by second line of Balmer series. Second line of Balmer series means Balmer series N1 value will be 2. Second line, first line should be from 3 to 2, this is first line, but they are second line, saying second line means you take it from 4 to 2 means this is the second line right now. So N1 is 2 square and N2 is 4 square, that's it. N2 square means 4 square. Okay, so by simplifying this, nu bar will be equals to RH X by 3 into 16, and here 1 by 4, this is 1 by 16. Next, nu bar will be X by 3 into 16, and this you can write 16, 4 is 4 minus 1, that is 3, that's it. Okay, okay, so next what we can do? Okay, so what we can do here? So we can remove this 3, this is RH, Z square is 16. Okay, 1 by N1. N1 value is how much? 2 square, and N2 value is 4. 4 square 16 I am taking here. So the next what we can get? LCM as 16 here I am getting, yes I am writing 16, and after that in 4 table we will get 16 at 4 times now. So here I am writing 4 minus 1, 3, that's it. Next nu bar will be how much? X into, so I can remove this 3, and the next 16, so we will get nu bar equals to X. Hope this is clear. I hope all the concepts that we have discussed here are clear. Now I will be telling you one more formula to use that will be related to energy. So what is the energy formula here we can use? Similar to this Rydberg's equation, you got one more equation, see. Energy difference, when an electron is falling from higher energy to lower energy, the difference will be there now, that will be taken in terms of joule per atom in this manner. See, 2.18 into 10 power minus 18, 1 by N1 square minus N2 square joule per atom. This will be the case in terms of joule per atom. If it is electron volt per atom, just take 13.6. Z square here you can use Z square also. Okay, Z square 1 by N1 square minus 1 by N2 square, this is electron volt per atom, that's it. These are the two formulas you can use for getting energy difference. Okay, there are a lot of questions related to these. Okay, so we will be continuing our discussion on this de Broglie wave equation and then next Heisenberg's uncertainty principle in the upcoming sessions. Okay, so once after completing all the sessions, all the discussions of this important topics of this structure of atom, then we will solve a special session includes all the PYQs. Okay, hope you have watched a complete session that we have discussed here. So if you are looking for a specific topic to be discussed, you just mention in the chat box. Our team will definitely look into it and will definitely consider to discuss in the upcoming sessions. Thank you for watching. Stay connected with this NEET World channel. Thank you.